students, welcome to the coordination chemistry class. Okay, this is the 16th lecture. See, in previous class you have studied the stepwise formation constant and overall formation constant and the relation between those, isn't it, those two. Okay, and we have concluded with, say, the factors affecting the kf values. Okay, and once again we recall, see, the factors affecting kf values, formation constant values, are statistical factor, steric factor and electrostatic factor. Statistical factor means in each step the coordinated water molecule is replaced, and as there is a decreasing number of coordinated water molecule, say, the stability constant will decrease. Okay, and the second one is, say, the steric factor. Suppose the entering ligand is bulkier than water molecule. Okay, and due to the steric hindrance, so due to the entry of bulkier group than the water, say, there is a steric hindrance between water molecules and the entering ligand, and thereby the stability constant decreases. And the third factor is electrostatic factor. Electrostatic factor is nothing but repulsion between the ligands. That means the ligands already present with the metal ion and the entering ligand. Okay, and thereby the stability constant decreases. Okay, so now with this we'll move on to the next one, the factors affecting stabilities of complexes. Okay, so there are many factors, okay, which will affect the stability of complexes. Okay, mainly we'll discuss regarding, say, the nature of metal ion, one, nature of metal ion, and the second one with regarding the nature of ligand. So under nature of metal ion, once again there are many factors. Say, oxidation number of metal ion, size of metal ion, ionization energy of metal ion, outer electronic configuration of metal ion. These are also plays a role in stabilizing the complexes, okay, or destabilizing the complexes. For example, and say oxidation number. Say oxidation number, greater the oxidation number of the metal ion, greater will be the attraction. So oxidation number greater means what? Which is having more positive charge, okay, and that will attract the negatively charged ligands fast or more or to the larger extent. Thereby the complex will be more stable. So for example, you are well familiar, FeCN6 plus 3 and also FeCN6 plus 2. That means in this complex the metal ion is in plus 3 state, and in this complex the metal ion is in plus 2 state. Therefore plus 3 state complex is more stable than plus 2. That means oxidation number of metal ion, it is here plus 3, here it is plus 2. So this is more stable than this. Therefore greater the oxidation number, greater will be the stability. Second one, smaller size. So smaller the size of the metal ion, say, greater will be the attraction for ligands, and thereby the resulting complex will be more stable. Okay, and the third factor is ionization energy. So what do you mean by ionization energy? It is the minimum amount of energy required to remove an outermost electron from a metal ion or from a metal atom, isn't it? If it is higher, that means it is difficult to remove the outer electrons, is it? That means it is having tendency to attract the electrons than to lose the electron. That means higher ionization energy means that metal ion is not ready to lose the electron, not to lose its electron. That means it is ready to accept the electrons. Therefore, say those metal ions which are having high ionization energy, which are having less tendency or less eagerness to lose the electron, and those metal ions are prefers to form a complexes with greater stability. Okay, the fourth factor, outer electronic configuration. Say you are well familiar, so there are complexes which are formed by transition metal ions, metal atoms, as well as non-transition elements. transition elements as well as non-transition elements. So usually transition elements form stable complexes because which are having say partially filled d orbitals, okay, and which will form the more stable complexes. And if you compare it with the non-transition elements, for example, say potassium forms the complex in its plus one state. So the K plus means what? It is having inert gas configuration, and that is same as that of argon, is it? So now with the stable electronic configuration, they will not form the stable complexes, okay, and thereby say the complexes formed by transition elements are quite stable than those formed by non-transition elements, okay, and that is due to outer electronic configuration structure. So with this we'll go for the second one, nature of ligand. So once again, nature of ligand includes once again the subfactors, nature of donor atoms, basicity of ligand, and chelating ability of the ligand. Say first one, nature of donor atom. Say the donor atom is more electronegative than the metal ion, then it forms the stable complexes or the stability of the complex increases. And the second one is basicity. Basicity means electron donating tendency of the species or the ligand is said to be a basicity of the ligand. So electron donating tendency. Say if the greater the electron donating tendency, greater will be the stability of that complex. Okay, so that means the ligands which are eager, which are having greater tendency of donating pair of electrons to the central metal ion, then the resulting complex will be more stable. So with this the last one, say the ligands which are bidentate or polydentate. So bidentate means what? The same ligand capable of donating two pair of electrons or which is having two donor atoms. They are said to be bidentate. Polydentate means these are the ligands which are having the tendency of donating more than two pair of electrons, say three pair of electrons, four pair of electrons, five pair of electrons, six pair of electrons, isn't it? And you are well familiar, EDTA is the single molecule which is capable of donating six pair of electron. It is a hexadentate. You are well familiar in the say fifth sem, isn't it? So now, so such ligands when they react with the metal ion, they form a ring structure. That means in the molecule. For example, bidentate. Say the ligand which can form two bond with the metal ion and then it is said to be bidentate. There is a ring formation. Okay. Or say for example, say oxalate. Okay. Say this is the oxalate bidentate and which can donate a two pair of electrons to the same metal ion. Is it? So now the complexes which contain such ring systems, they are said to be say chelates. Chelates are nothing but these are the complexes formed by bidentate or polydentate ligands, and the ligand complexes which are having such ring structures, they are quite stable. Okay, so these are the some factors which will affect the stabilities of complexes. Okay, we'll discuss in the next class. Thank you.